Welcome! We're going to work on solving some exponential equations, kind of continuing off from class today. So we're going to start off with the example 5 to the x equals 30. What I want to stress to you right now is there's kind of two methods we could use. The first method, which is kind of the common core method, is to rewrite this in log form. Knowing this, we could say the log base 5 of 30 equals x. I know this is the correct form because I can just kind of go do my swishy thing. 5 to the x equals 30. I also remember that the base 5 goes in the basement and the exponent x goes all by itself in exile. At this point, I could take my handy dandy calculator and I could go control log base 5 and go over to 30 and get my answer, which is 2.11, which of course you can see rounding. I've decided for this video we're going to round to the nearest hundredth. So with that said, I'm going to say x is approximately 2.11. To be quite honest, that's a really great method for doing it. It's not traditionally the method we've done before this class, so I want you to be aware of both ways to do this problem. With that said, in class today we talked about how when we want to get rid of having the variable in the exponent, there's a simple thing that we can do to both sides that will take that exponent and move it in front. So what is it, guys? Yep, it's taking the log of both sides. So if I do that, I'm going to get the log of 5 to the x equals log of, 30. At this point, the x can be moved to the front, and we're going to have x log of 5 equals log of 30. Now when we divide, we're going to get log of 30 over log of 5 is approximately x. We're going again for an estimate answer, and you can see on your handy dandy calculator that if I do the log of 30, and I'm going to do this base 10, I want you to notice that I logged base 10 each side, divided by the log of, that's a little typo there, the log of 5, again we get the same answer, 2.11. So with that said, both methods will give you the same answer. Now I know you're looking at this and saying, why would I ever use this second method? The second method leads into something we call the change of base formula. And again, the first method might be expedient, but the second method is going to be something I think that as your math skills develop, you're going to find in calculus you're going to do quite often when you want to find a derivative or a log and have to change a base. Okay, so with that said I want you comfortable with the second method too. And notice also that when I chose to log both sides, I did it base 10. I could have used any base I wanted, but that's the one I chose to use. I'm going to stop the video now and have you try one. For our next example, we're going to go ahead and we're going to solve for e to the x equals 5. Now in this case, I'm going to start off by isolating the e to the x by dividing both sides by 4. That's going to give us e to the x equals 5/4. At this point, again, we have two options. The first option is to rewrite this in log form. If I were to do that, I would see that naturally, if the base is e, I'm not going to use common log, I'm going to use natural log. So the natural log, and now I'm going to think here to myself, the exponent goes in exile by itself, so it's going to be rewritten as the natural log of 5/4 equals x. And this is beautiful. I go to my handy dandy calculator and I'm going to hit the natural log, and I'm going to do this as a stacked fraction of 5 over 4. and I'm going to get approximately 0.22 when I round to the nearest hundredth. Now again, I can do this a different way by taking the log of both sides. I would start the problem exactly the same way. I would divide both sides by 4, get e to the x equals 5/4, but now instead of logging base 10 each side, because of its e, the inverse would be ln. So I'm going to do the natural log of both sides. That's going to have the desired effect of moving the x in front. And that's going to give us x ln e, but the ln e of it is just 1. So I'm going to have x equals the ln of 5/4, which is the same answer we got before if I round it to the near hundredth, or nearest hundredth is about 0.22. Again, I'm going to stop the video and have you try one or two just for a little bit of practice. Good luck! Last example, we're going to go a little bit out there. Here we go. We're going to start off with something that looks like e to the 2x minus e to the x minus 6 equals 0. Hopefully some bells are going off in your head. This kind of looks like something squared minus something minus a constant. Can we rewrite this in quadratic form? Okay, so thinking like that, I'm going to do a u substitution. I'm going to let u equal e to the x. Therefore, u squared is e to the 2x. So this problem is going to be rewritten as u squared minus u minus 6 equals 0. When I factor that, it's going to factor into u minus 3 times u plus 2 equals 0, giving us u equals 3 and u equals negative 2. However, we don't really care what u is. What we care about is x. So I'm going to replace that u with e to the x equals 3 and replace this u and get e to the x equals negative 2. Again, to solve this, I can natural log each side. And if I do that, I'm going to get ln of e to the x equals the ln of 3. And I'm going to get ln of e to the x equals the ln of negative 2. This side gives us x equals ln of 3. And this time I'm going to leave the answer exact, because whenever I round to the hundredth, I'm actually getting an estimate. And this time I'm going to stress that sometimes we want an exact answer. And this one's going to be interesting, because if I go into my handy-dandy calculator and I hit ln of negative 2, the calculator sends me an error message. And that's because if you think of an exponential function and you think of the base here, there's no way to raise e, a positive number, to a power and get a negative answer. It just can't happen. E to the x is never negative 2. It's never negative, period. Therefore, this leads to no solution, and we only have one solution, and that the exact answer is x equals ln of 3. With that said, I'm going to leave you with one more to try, and we'll talk about these and some similar examples tomorrow.